So in the last two lectures, we studied conjugate direction methods, the basics and the powers method here, and in the next, the conjugate gradient method. Conjugate gradient method uses just the gradient and line search. Using the same, there is another method or another class of methods called Quasi-Newton methods. That is the subject matter of the present lecture. So first we will study the idea of inverse Hessian construction through updates, and then we will look at the well-known Quasi-Newton methods, DFP and BFGS methods, and then we will briefly discuss the properties of these methods. So the idea. We have seen that in several methods, like steepest descent or conjugate gradient, these two are common operations. Gradient evaluation at the x value in an iterate, and then based on that, a direction is generated along which there is a line search and update to the next iterate, where the similar things are followed. It is only the manner in which the next direction is generated that these methods differ among themselves. Now, if this much is being done, that is x is changed and the gradient changes because of that over the steps, then with this much information in stock, we can actually infer the Hessian based on the change in x and the corresponding change in gradient. We do not need second derivative evaluation to evaluate the Hessian. We can infer it from these step changes. So suppose we denote by pk the step in the solution space x from one iteration to the next, which is actually alpha k dk, where dk is the search direction from xk to xk plus 1. And since we evaluated the gradient at xk earlier, and after completion of the line search, we are evaluating the gradient at xk plus 1, so we can subtract them to find out the corresponding change in gradient and call it qk. Now, if with this much change in x, this much change in gradient takes place, then Hessian must be a matrix which multiplied with delta x gives us delta gradient. Okay? Or if we denote the Hessian inverse by b, then it will be bqk equal to pk, like this. This should be approximately equal. Either you say this or you say this. It means the same thing. So H is the Hessian and B is the inverse Hessian across this step. That is the representative Hessian for this step and the corresponding representative inverse Hessian. So with this kind of information, through every step, we get one unit of information about the Hessian or inverse Hessian, whichever one you want. With lots of steps like this, we get lots of such information. Okay. So in principle, with n or more units of such information, we should be in a position to construct the matrix completely, because the matrix is n vector worth of information, and through every step we get one vector worth of information. Okay. So let us see how. Say with such data over many steps, we can construct H or B. In the case of quadratic function, exactly, for which this remains constant, and otherwise approximately. A very rough and crude and down-to-earth way of this would be to collect n steps like that or more, and then collect such equations, n or more such equations, BQ0 is P0, BQ1 is P1, and so on. Now, when there are at least n columns here and the corresponding n columns here, then you have enough information, because with n columns, this as well as this become square matrices. And if the columns are linearly independent, then you can invert this to get B, right? So invert this and post multiply on this side. So this is a crude way of doing it, and you can do it only after you have collected n such steps of information. But actually, this is not how it is done. How Quasi-Newton methods, or the so-called variable metric methods, do it is that over individual steps, they work out an update and add it to the previous matrix approximation. Okay, very much like Broyden's method of solving nonlinear systems of equations. So like that, starting with one such matrix, calling it B0, over every step, one such update is added to improve it, improve it, improve it through steps. That is what Quasi-Newton method does. And every improvement is made based on the current vectors Pk and Qk for that particular iteration. So over every iteration, the approximation of this unknown matrix becomes better. So the simplest that you can think of, we'll see that. Say, let us see with that inverse Hessian constructed through updates what we can achieve. A Newton's method step operates as dk is equal to minus Hessian inverse into grad. So if you can approximate the Hessian inverse, then in place of Newton's iteration, you can place that. That is why it is called Quasi-Newton methods. Okay, and this Quasi-Newton method will do a similar thing like Newton's method without actually computing the second derivative to evaluate the Hessian matrix. And it will not have to invert the matrix or solve the corresponding linear system, because rather than updating the Hessian, we can update the inverse Hessian itself. It is the same cost or same complexity. So now, if the Hessian or its inverse, whichever you take, I mean, if the Hessian has negative or zero eigenvalue, then its inverse also will have. So if the Hessian and therefore its inverse in the neighborhood happens to have any negative or zero eigenvalue, then rather than getting the correct evaluation or correct estimate of it, we would rather prefer to operate with an approximation of the inverse Hessian here, such that the approximation is positive. The approximation has all positive eigenvalues. So this is the idea. In the pure Newton's case, where you evaluated the Hessian, you did not have any direct control over that. Now, very much like the Jacobian construction in Broyden's method, we can apply suitable updates. Just a minute. However, with Broyden's method, here we have two differences. One is that in the case of Broyden's method, we were constructing Jacobian, which had no compulsion to be symmetric. But here we are constructing the inverse Hessian. So Hessian as well as the inverse Hessian is a symmetric matrix, and therefore our update also will be symmetric. Second difference is that In the Jacobian construction of Broyden's method, we supplied the correct Jacobian in the beginning. Okay. Here we don't want to do that. I mean, we don't need and we don't want, because if the correct Hessian there happens to be indefinite, then we will end up giving that indefinite Hessian or its inverse to begin with. And it's not good to seed the process with an indefinite Hessian. Any negative eigenvalue will be harmful. So we start with a positive definite matrix. And to start with, we don't care whether it is the correct Hessian or not. In general, it will not be correct Hessian because we don't know, or its inverse. So we start with an identity matrix as the starting approximation of the inverse Hessian. Okay, an identity matrix is certainly positive definite. So the simplest update, simplest correction would be a rank 1 correction like this. And note that here we are using AK, ZK, ZK transpose. In the case of Broyden, these two vectors were not the same. It was UV transpose kind of thing. But here the two vectors are same because we want a symmetric update, because the matrix has to be symmetric. So this is the proposal that we make and then force the condition that this updated matrix should actually behave like the inverse Hessian on the current step, the equation that we saw. That is, this B operated over the current Q should give the current P. Okay. So this Bk plus 1 Qk equal to Pk. Force it, thereby determining this. So multiply this with Qk. So you get Bk Qk plus this whole thing into Qk. In this, in the associative matrix vector product, the last bit zk transpose qk is actually a scalar. That's why to show it separately, we have got this in parentheses. So ak is also scalar, this is also a scalar, the only vector remaining is zk. And this whole thing should be equal to pk according to this. And that means that this term, which is the only term containing any unknown, is pk minus this. That is, this term which has the unknowns is pk minus bkqk. Call this whole thing which is known as rk. And now do two things. Take the product of rk with rk transpose on this side, which will become a matrix because this is a column vector and its transpose will be a row vector. When you multiply, you get a rank 1 matrix. So rk transpose will be ak is scalar, this is also scalar, so these things will just get squared. And the vector part, zk transpose, this is the matrix. So this scalar, ak square, zk transpose, qk whole square, this scalar times this matrix is this. And on this same equation, rk equal to this, take inner product with the vector qk. Then on this side you get qk transpose rk, that is this. On this side you get this scalar into this scalar into zk transpose qk, which is this scalar once more, and therefore you get this. Now you see that if you divide this matrix with this scalar, then you get exactly what you wanted, lock, stock and barrel, because one AK will go off, the other AK will remain what you wanted. This ZK transpose QK whole square totally will go, and ZK transpose will remain what you wanted. So this right side divided by this right side will give you just this update, something that you wanted. That means RK transpose divided by this scalar on the other side, which you completely know. So this determines our rank 1 update completely. And therefore, the updated matrix will be bk plus 1 equal to bk times this is rk transpose, this is qk transpose, this is rk. So this is the formula for the rank 1 update. Now, pk is a step at the kth iteration. If bk were the correct inverse Hessian, then bkqk would be equal to that. In that case, it would be 0. So that means this vector on which the correction is driven will be 0 after the inverse Hessian has got constructed correctly and completely. And then no more update will be needed. Now, this looks very fine. Okay? And you can also check that indeed this correction or this update behaves as, this updated matrix, this update behaves as true inverse Hessian, not only on the current step QKPK, based on which it was determined, but also on the previous steps for a quadratic function, for which the Hessian and therefore the inverse Hessian does remain constant. So you can show that for a quadratic function, this bk plus 1 operates like the inverse Hessian not only on pk but also on the old steps. So suppose for the time being that Hessian h is constant and positive definite. Then rank 1 corrections, a series of them, do build up the inverse Hessian correctly over a sufficient number of iterations, n of them. To check that, we will check this, whether this operates on qi and gives pi for all the steps. This matrix is the last one that we have just calculated, and we will operate it over all the old steps. So the proposition is certainly true for k equal to 0, because for k equal to 0, only the current step is there. Okay, q0, p0. So b1 q0 equal to p0. Based on that only, the update has been determined. So this will be obvious. So the proposition is true for k equal to 0. Taking that as the seed for our induction argument, we assume that the proposition holds for k equal to j, that is bj plus 1 qi is indeed pi for all the previous steps, all the previous i's. Okay, for I equal to 0, 1 up to j minus 1 and the current one, j, indeed. Then we check it for k equal to j plus 1, whether it is true for j plus 1, whether that is implied by this. So with constant Hessian h, whatever pi you take, hpi will be qi. B is getting constructed, h is not known, not constructed, but there is some h in the background. Okay, so hpi is qi for a constant positive definite Hessian. Now we want to check for k equal to j plus 1, right? So here it will be bj plus 2. Bj plus 2 qi equal to, according to the formula, bj plus 1 qi into the rank 1 update formula, rr transpose by q transpose r for j plus 1 into qi. So this is correct pi because of the induction hypothesis that the proposition holds for k equal to j. This one is here. Rj plus 1 sitting as it is, the denominator sitting as it is. This one is Rj plus 1 transpose Qi. Now, look at this carefully. Rj plus 1 is Pj plus 1 transpose Qi. I mean, this Qi is here. So, Rj plus 1 is the formula we have used, P minus Qb. So, P transpose Q minus Q transpose BQ. Okay. So, because Rj plus 1 is Pj plus 1 minus Bj plus 1, Qj plus 1. So its transpose gives you this. And the Qi is sitting as it is. Now, This one you retain as it is, and this part bj plus 1 qi, the way you put here pi, here also you put it pi bj plus 1 qi, because the induction hypothesis gives that directly. And what you do, this qj plus 1, from this definition you write as h times pj plus 1. You see, for bq equal to p, you can get only for those indices which the induction hypothesis has given or you have shown, okay? Because this is something which we are constructing. Regarding hp equal to q, you can put it everywhere, because h is Hessian and this is the correct Hessian, and this is the definition of the Hessian, okay? So for this qj plus 1, we are writing h times pj plus 1. Now open this transpose. You get pj plus 1 transpose here. This term has been kept as it is. This is pj plus 1 transpose into h. H transpose is h because it is symmetric. So that hp1, hpi, now put qi, and then you see this is 0. So this term indeed is 0. So this term here is 0. So this term totally is 0. And therefore, bj plus 2 qi is pi for every I. Okay. So this shows that this rank 1 update operates as the correct inverse Hessian, not only on the current step, but on the previous steps as well. Okay. So this works to that extent. So the rank 1 correction is successful in constructing the inverse Hessian correctly. For quadratic function, convex quadratic function we have shown, but that means that also means that close to convergence near a minimum point, it will be so for any matrix, any function. Okay. However, there is a big problem with rank 1 correction or rank 1 update. It may fail to ensure continued positive definiteness. Even if bk is positive definite, there is no guarantee that bk plus 1 will turn out to be positive definite, because the scalar in the denominator that you have got, this qk transpose rk, okay, that is actually a little awkward. This term, okay, there is no guarantee for this term to be this scalar, entire scalar, to be positive. And therefore, even though above you have a matrix, the worst eigenvalue of which will be 0. In fact, this is rank 1, so only one eigenvalue will be positive, all others are anyway 0. But there is no negative eigenvalue. Okay. But if this becomes negative, then there will be a damage to the earlier bk. Even if the earlier bk is positive definite, because of a negative number appearing in the denominator here, the diagonal entries of this will be negative, and in the sum, the diagonal entries may decrease, and that is dangerous. That may take you towards indefiniteness or towards singularity, which is the same direction. So this is a serious problem with rank 1 update, because the general methods are for general problems and not for only convex quadratic functions. And therefore, the actual Quasi-Newton methods work with rank 2 corrections or rank 2 updates like this. Okay. So in the rank 1 update, we have seen one term based on pk, another term based on bkqk. The same things with some scale, if you put it as zk and wk here, then you get one straightforward rank 2 update, one straightforward Quasi-Newton method, which is this: pk transpose divided by pk transpose qk minus bk qk transpose bk divided by this. Completely symmetric, except that this is a minus sign here. Okay, this is a plus sign. So with the claim for DFP method, Davidson-Fletcher-Powell method, is that if you start with a positive definite matrix, the resulting updated matrix also will be positive definite, certainly. Okay. Apart from enhancing the applicability of this updated matrix over the iteration for one more dimension. Okay. Because one more step would be included now in the correct behavior as inverse Hessian. So this is a successful method. It works. Now the derivation of this important result and also the other important result that it does behave like inverse Hessian over the previous steps. These we will defer. Before that, we see all the rank 2 updates which are in use. There is another famous Quasi-Newton method that also is dependent on a rank 2 update, that is called Broyden Fletcher Goldfarb Shannon method, BFGS method. Now, both the inverse Hessian updates that we have seen earlier, rank 1 update and DFP update, operate on two vectors, pk, the step, and bkqk, what the step would be if bk were the correct inverse Hessian. Okay. Now, a rank 2 update similar to the DFP formula, but not on the inverse Hessian, but on the Hessian, would look like this. From that formula, the DFP formula, here we have interchanged P and Q and put the Hessian H in place of the inverse Hessian B. Okay, because their roles are reversible. That is, in the formula, if you just interchange P and Q, H becomes B, B becomes H. Now, if the rank 2 update on the inverse Hessian was acceptable, then this rank 2 update on the Hessian itself would be acceptable. However, it would not be a very nice idea to first operate like this, get the Hessian estimate, and then actually solve this linear system, okay, to get the direction. Because in the alternative, we were directly getting the inverse Hessian, which we were just using here to multiply. And you know that matrix vector multiplication is a much cheaper operation compared to solution of a linear system of equations. So this will not be computationally competitive. So what this BFGS method working for this in the background does on the foreground is that it actually works out an update on the inverse Hessian, a rank 2 update on the inverse Hessian, which is equivalent to this rank 2 update on the Hessian itself. How to do that? We know that rank 1, rank 2 kind of updates can be incorporated analytically in the inverse directly. For example, if you have a matrix A for which you have already calculated A inverse, okay, and now in the matrix there is a correction like this where U has 1 or 2 or 3 columns and V also has that many columns. So UV transpose in that, say 1 or 2 or 3, say P columns. So U has P columns, V has P columns. So V transpose will have P rows. So the matrix U will be N by P, matrix V will be N by P. So V transpose will be P by N. So N by N into N by P into P by N. So it will be N by N, which is the same size as this. So if there are a few corrections like this, P corrections, then the corrected matrix inverse you can get from this formula, which is the Woodbury formula, which is actually a multidimensional generalization of a single update formula, rank 1 update formula of called Sherman-Morrison formula, which operates as for a single vector like this. Okay, and this formula you can actually prove. You can expand this and then After opening out, manipulate that series a little, and then collect again infinite terms to get this inverse, and you can show it. And this inverse actually can be found by analytically inverting this little p by p matrix. This should be IP, not IM. Okay, this is a typo. Okay, so, or I mean, you can prove it like that. You can derive this inverse formula analytically, or you can actually multiply this matrix, this big matrix, this expression with A plus UV transpose either on this side and on this, or on this side, and in both cases you should get identity. Okay, if that comes out, then you know that inverse of this is this. Okay, I think you should do this exercise to verify that it is really the inverse formula for this. Okay, so here P is 2 because it's a rank 2 correction. There are two corrections, one PK transpose, the other, or rather QK transpose, the other HKPK and its transpose multiplied. Okay. So P is 2, A is HK, A inverse is its inverse, which is BK, which will be updated. A plus UV transpose is the HK plus 1, and you want its inverse, that is BK plus 1. So you apply the U and V, you take U and V appropriately so that UV transpose turns out to be this and that. So here it is plus, here it is minus, and that is why in the U and V, in one of them, the second column is negative, in the other it is positive to get this minus sign correctly. And you see this QK transpose by PK transpose QK. The split, the column in the U matrix and column in the V matrix, either you can keep QK in one of them, and in the other you can keep QK by PK transpose QK full. This is scalar. Or you can split degrees half of QK by square root of this and QK by square root of this. For that, you need to know that this is positive, okay, which I have done. But if you are not very confident of taking this as positive, that you can take its square root, then you can club this entire scalar on one side. Similarly, this entire scalar on one side. On one side, you can keep just minus HKPK. On the other side, you can keep plus HKPK by this entire scalar. You can do that asymmetric thing. It will finally give the same result. What in this slide I have done is that split one mu here and the other mu here, and mu square is 1 by this. Similarly, one nu here and the other nu here, and mu square is 1 by this, what was in the denominator there. This argument you can use only if these two things are positive, you know. But till now, we have not established it. So if you want, you can keep the entire scalar on one side, in which case you do not have to bother about positivity and square root and so on. Okay. So this also you can do like that. You take and see that you finally reach the same result. So this is basically to work out the updates. And then all these things you put in this formula to get BK plus 1. The steps are here. Okay. So BKU into I2 plus V transpose A inverse, which is BKU inverse of this 2 by 2 matrix into V transpose BK. Okay. So if you work it out step by step, so at your leisure, you go through the steps properly. This is just matrix algebra, nothing. Okay. So finally, you get this huge update formula. This is called the BFGS update formula. Now, why do so much of gymnastics if we had the competing DFP formula? Actually, you can do most of your good work with DFP formula itself. You don't need this. But because the qualitative properties of both the formulae are similar. However, numerical studies show that this BFGS formula works somewhat better. So by evaluating this sandwich 2 by 2 matrix inverse, and then we multiply the three matrices together to get this. Okay. Now, since both the updates on BK, the DFP update which we saw earlier, which was simpler compared to this, and this BFGS update, which apparently works better as shown by numerical studies, you can also combine the two update formulae like this by a convex combination. 1 minus phi times DFP plus phi times BFGS. And with continuous values of phi, non-negative. Okay. You get continuous rank 2 updates. And this entire continuous rank 2 updates, this family is known as Broyden family of methods. Okay. So for phi equal to 0, you will get the DFP update. And for phi equal to 1, you will get the BFGS update. So the entire continuous spectrum is fine. In fact, over iterations, from iteration to iteration, you can change the value of phi, okay, continuously or by discrete steps. You do as you please. Okay. Now, if in the Broyden family of methods, in principle, you can change the value of phi across iterations with a constant value of phi, whether it is 0.2 or 0.5 or 0.8, you get a Broyden method. Okay. With phi equal to 0, you get the DFP method, which is also a Broyden method. With phi equal to 1, you get BFGS method, which is also a Broyden method. So Quasi-Newton methods in general you can call as Broyden method. Okay. Now, getting all this together, put the steps which you can use to write a little program or use in your calculation directly. Select suitable tolerances for change in x and the gradient norm. Initialize the initial inverse Hessian estimate as identity. Select the initial point. Evaluate the function and gradient at that point and start iterations. The first step would be to get the direction. Initially, you know that since B0 is identity, so initially you will get the negative gradient as the direction. Okay. But this BK setting here is important for next or later iterations. Okay, when BK will be updated. Along this direction, conduct a line search. The change, the delta x is alpha k dk, and update xk plus pk. Okay. And then at the new point, evaluate the gradient fresh. If that gradient is very small, then stop. Else, update q. Okay. The difference in gradients from the previous point to the current point. If any of these changes, either change in x or change in gradient, is very small, this you compare with epsilon x, this you compare with epsilon g, right? Because the scale may be different. If any of these turn out to be extremely small, then stop. This is the main stop. Okay, that means you have converged. This is the subsidiary stop, which means that not much progress will happen in future. Okay. I mean, that also quite often means this, but it may come from here. After you have got both PK and QK, which you need along with BK to get BK plus 1, apply the correction in the inverse Hessian estimate. That is, evaluate BK plus 1, either by the DFP formula or by the BFGS formula or the combination, Broyden method. And then increment k and start the next iteration from step 3. Now, among these, there is not much of a difference in most of the cases, particularly with exact line search. Only when you conduct inaccurate line search, there would be a difference among them. Okay. And BFGS would typically perform better than this. Okay. So otherwise, all of them are more or less similar. Now, briefly, we discuss the properties. Through all these Quasi-Newton methods, rank 2 updates, based on rank 2 updates, what will be the property? One very, very important property will be that a positive definite BK will always give a positive definite BK plus 1. And therefore, if we start with a positive definite B0, as we do, because identity matrix, our typical B0 is positive definite, then the positive definiteness is sustained through all iterations. This will happen irrespective of what kind of function it is. Okay. It doesn't have to be quadratic function. It doesn't have to be convex everywhere. It doesn't have to be convex at the present operating region. But the inverse Hessian estimate that gets constructed from an initial positive definite seed will always be positive definite. Now, these things will happen for a convex quadratic function in which Hessian H is positive definite and constant. And therefore, these things will also happen for any function close to a minimum point, where on a small neighborhood, H can be taken as constant, and around the minimum in a small neighborhood, it is positive definite also. And therefore, these things are important for any function for the purpose of local convergence. Okay. So successive directions are mutually conjugate, implying this. The two steps, any two steps for I not equal to j will be conjugate with respect to the constant Hessian. Okay. Therefore, Quasi-Newton method actually inherits the properties of a conjugate direction method. Now, there is another kind of conjugacy exhibited in Quasi-Newton method. Every gradient change, Qk, which is this, also exhibits a kind of conjugacy with the older steps with respect to the current inverse Hessian estimate. This is taken as constant. So it's for all pair. This is for these steps of Qk with the current inverse Hessian estimate. Okay. And the inverse Hessian estimate correctly maps each step till that point. So for all I up to k, this will be correct. This inverse Hessian mapping correct. So that means in n steps, n linearly independent steps, the inverse Hessian gets completely constructed. And therefore, in at most n steps, the method converges to a minimum point for constant Hessian, constant positive definite Hessian. And therefore, after the iterates have come close to the minimum point, this is bound to happen for any function. Now, let us have also a quick look at the convergence properties. Even if the objective function is general and the Hessian at a particular iterate is not positive definite, even then, the Quasi-Newton rank 2 update on the inverse Hessian is bound to be positive definite. Therefore, this direction, which is minus positive definite matrix into this, will be a descent direction. This we have checked in the case of Newton's method, right? That if the inverse Hessian is positive definite, then it is a descent step, because as you take inner product with grad f, on this side it will be a minus positive number. Okay? So the global convergence is guaranteed. There is no problem there. In later iterations, near a minimum point, the actual Hessian will have positive definiteness or will approach positive definiteness, and the inverse Hessian construction will improve its accuracy. Okay? Because the steps also will be small. then the search direction decay will approach the Newton's direction, and hence quadratic convergence. Okay. So eventually you will get quadratic convergence. Now, even in the earliest iterations, the local convergence is at least as good as the steepest descent speed. So overall, in the beginning, as good as or a little better than steepest descent, towards the end, approaching Newton's method. Overall, the speed of convergence is called superlinear. Okay? So this is how Newton's method operates. And the Quasi-Newton method operates. So till now, Quasi-Newton methods are by far the best algorithms in terms of effectiveness and efficiency. However, since Quasi-Newton method needs to store a matrix, the inverse Hessian estimate, so in large problems, its storage requirement may be high. In that one count, in large problems, conjugate gradient method may have an advantage over Quasi-Newton methods. Otherwise, so far as effectiveness and efficiency is concerned, Quasi-Newton method beats all methods. So to summarize, note these points. Simple rank-on correction, which we first started with, can build the inverse Hessian accurately through line search steps, but there is no guarantee on positive definiteness. Therefore, for practically implementing it in a program, you cannot use it because global convergence does not get guaranteed. The rank 2 based Quasi-Newton methods satisfy both the requirements: continued positive definiteness as you start from a positive definite matrix, and inverse Hessian construction correctly over previous steps. And that means over n steps over which the Hessian remains more or less constant, it will get you the correct inverse Hessian. And these favorable properties of Quasi-Newton methods, which make them the champion methods of nonlinear optimization, they are supported by a deep theory on how these updates really work. And a snapshot, a cross-section of that deep theory we will discuss in the next lecture. For the time being, we stop here.